Thank you. Actually, I didn't check if this was working, and I plugged in this one. I don't know if there is but actually, I can just use the fingers. Yeah, I will use the fingers. No worries. Okay. Okay, but it's just for the pointer actually. So yeah, I can use the finger. It's just for the pointer to. Okay. Oh, excellent. Perfect. Thank you very much. Thanks. We're good? Okay, so I decided to talk about a topic that I really enjoy myself, which is about the metric of our local universe. I like it because it's kind of a sensible question that I asked myself for my whole life, even before becoming an astronomer, like asking where I am and where are we going. So I hope that by the end of these two lectures, today and tomorrow, you will get an idea of at least what I've been done for the past 4 years to try to answer this question. Okay, so just to give some scales in perspective, we are more or less close to the Stadio Palestra Italia, and since I'm Italian, this is a palestra, I thought it was interesting to use this image. And this place is located more or less here around the Milky Way. And these images are not in scale, as you may imagine, but even the Milky Way is a rather small dot that you can see here in a very obscure large-scale structure distribution. This is not so big. It's going to be like 300 megaparsec, more or less, in terms of linear scales. And these weird lines here are called streamlines, and are lines of the velocity field. Now, this is the most recent reconstruction of the local universe we have, and this is from Valade et al. It's taken from a Cosmological 4 catalog of peculiar velocities. I will explain what these type of plots means tomorrow. Today is going to be much more old school and pen and paper about what we know about structures formation in lambda CDM and analytical models we use to try to understand what these structures are. Okay, so just to keep the analogy about the scales, we know that we have like these type of scales that we try to describe in physics. For the first years of your undergrad, you probably use this type of scales here, or smaller if you then moved on and studied particle physics and quantum mechanics. But for what concerns astrophysics, then we have a very wide range of scales in which we speak about distances, but we actually don't have much control over those scales, at least from a theoretical perspective. What do I mean with that? Is that to discuss distances, we use general relativity or special relativity, depending on the limit. And for these type of discussions, we need a metric. Otherwise, defining the distance between the points is very hard. And you know, on Earth or like on these solar system scales, we use kind of a perturbed Minkowski metric, and that's more than enough. When we go to a bit larger scales, we have maybe Newtonian physics, so some perturbed Minkowski that is still valid, or maybe not, because, for example, there's a lot of people like Galloppo, which is a PhD student, or Wilshire, or Torrieri, which I don't know where it's based now, that are trying to say maybe this type of dynamics is not well described by Minkowski, and you have to keep into account rotational effects, and they might be, you know, responsible for what the apparent rotation curve of galaxy is. So maybe they will explain that matter. I don't think that's the case, but it's just to stress that it's important to keep into account that we are using metrics on these scales, but we don't really know which one we should use. And then we finally go to cosmological scales, where we are sure, more or less, that perturbed pre-barometer overkill is a correct description of the universe. But again, this is more a hopeful hypothesis, not a well-understood theoretical question. And I'm going to say a bit more about what I mean with hope, because, okay, it's called cosmological principle, not cosmological theorem. Okay, also another thing, most of these scales, we use perturbed Minkowski, so we say that the space-time is essentially empty. But of course, when we go to bigger scales, we cannot assume that the space-time is empty. There is a contribution to the structure of the space-time from the energy momentum content. Okay, homogeneity scale. And why is this important? Well, because at face value, we can observe only a two-dimensional projection of the sky. So we speak about a three-dimensional universe, but everything we have at the end of the day is dots in the sky. And to go from dots to something that is mapping a volume, we need to rely on cosmological stuff that has standardizable properties. So we need measures of distances which are reliable. And these standardizable properties used properly allow us to do number counting of sources and power spectrum, like Stefano discussed today, any type of summary statistics, and then we can infer what is the matter and velocity field. Now, this 2D to 3D conversion is where the devil is in the details, because, okay, what is a meter? We know that the meter is a certain displacement that is run by light in a second. And what is a second? A second is much more easy to understand in the sense that we can at least take an atom and see how many times it oscillates. So we have a definition of second on Earth, which is kind of reasonable, but the two, of course, in a curved space-time become very observer-dependent concepts. And what do I mean with that? That in GR, essentially, both the meter and the second are quite ambiguous, because even in vacuum, what is vacuum in general relativity? I mean, the fact that R, the Ricci scalar, is 0 does not imply that the space-time is empty. And not even that the space-time is flat. Sorry, it implies that it's empty, but not that space-time is flat. In order to be empty, is the full four-dimensional Riemann tensor of lambda, mu, rho, ni, that needs to be 0 everywhere. But we can have these different from 0 and are equal to 0. So this is just to say that it's a bit of an ambiguous concept to say what empty is in special relativity. And so when we, in general relativity, and so when we measure distances, which are, again, defined by light propagation, which means the line element equal to 0, what are we putting here? So this is kind of the context, and what I'm trying to say is, if we want to map the universe nearby us, at least the one nearby us, we need some type of metric to plug in this equation. So that's why we cannot put in distances. And which metric is exactly what I think nowadays it is possible to understand using real data rather than assumptions like the cosmological principle. Okay, why bother? Because we have an excellent model of the universe, which is the lambda CDM. You might have seen this plot many times in your life. Again, this is the angular power spectrum of the temperature fluctuations of the cosmic microwave background, and is the blue line is not a fit, it's a theoretical prediction from 6 parameters. So it's the best fit, but it's again from a theoretical model, which is reasonably well understood if you have dark energy and dark matter. So it seems to say, since this model is based on Friedmann-Robinson-Walker with some perturbation, it seems to be not really meaningful question to ask why we need a metric of the local universe if we know that the universe works very well on this case. Well, because that's not so true. We have a lot of tensions, or at least problems in the standard model of cosmology, the Hubble tension, sigma 8, so it's sigma 8. We have the evidence for dynamical dark energy, anomaly large dark flow, dipole tension, and growth rate tensions. So I don't want to spend too much time on this, but at the end of the day, we kind of have some tensions in the standard cosmological model, and so my question is, can this tension be described by the fact that lambda CDM at late times is not so good anymore? Because, okay, as I show you from the Planck plot, it's very efficient in describing the perturbation of the cosmic microwave background. But then, you know, we are taking cosmological information from a photo, essentially, a two-dimensional thing. But at late times, you have a cosmological volume of inhomogeneities, and maybe those are responsible for some of the problems we observe in the lambda CDM. And that's why I think when we perform measurements on this region of the universe where we live, maybe we need to take into account the impact of structures and the metric we should use to compute distances. Okay, so this was a rather long introduction. I apologize for that, but this is more or less the plan for the next two lectures. I will try to go through this very textbook stuff today, and then tomorrow going through this stuff to just show some hands-on work that I've been doing recently or that is being done, but a lot of people even clever than me. With a little spoiler, I decided, since I'm going to talk about strong back reaction and none of these is really about that, that this subject here, nonlinear analysis on effective fluid, I might discuss it today if I have still time at the end. So, plan for today is some review of structure formation in LMCDM, a review of what back reaction is, and then maybe an example of back reaction from my own research. Okay, spherical collapse on the blackboard. And why on the blackboard? Because I think it's cool. It's okay. I can use my thing. Okay. Thank you very much. To explain structure formation, we usually consider perturbations of dust. So we assume that the metric is just the standard perturbed Friedman-Robinson walker in the Newtonian gauge. So we have a tube psi here. There will be a delta ij, the xi, the xj, a squared. And then 1 minus 2 phi, the gravitational potential. So we have this line element, and then we consider perturbation of dust, which we write essentially by saying T rho rho is equal to just some background dust plus delta rho. We put T 0 I and T ij to be rho plus P. To 0 and this V I, and I'm forgetting an index J somewhere. It's the opposite. I guess it's the opposite. It's rho plus P. Exactly. Thank you very much. And T I J is basically given by P I J. Apologies. Yeah. The anisotropic stress, so the non-diagonal part of the spatial metric. Now, luckily for dust perturbation, we usually neglect this. And so with just these two plugged in the Eisenfield equation, we can build all our cosmological perturbation theory, which basically relies in two equations. One is the continuity equation, which is just rho plus 3 h rho. It's just dust equal to 0, which becomes delta dot plus gradient of V equals to 0, and then the Euler equation, which contains information about V dot, but since I'm not remembering exactly the equation, I will avoid writing it down. Okay, why I'm saying all of this? Because to understand the process of structure formation, we combine the continuity equation and the Euler equation to obtain an equation which is very simple, remarkably simple, which is delta dot dot plus 2h delta dot equals to 4 pi g rho delta. And we assume usually matter domination, so we say that h is just 2f3 divided by t, and rho is just 1 divided by 6p g t squared. And then we look for solution of the type delta is equal to t to the p times some delta 0. And if we look for this and plug it in this equation, we find a remarkable solution for delta, which goes as t to the 2 over 3, so which goes exactly as the scale factor. Now, why I have annoyed you with all these formulas? because this result, the fact that the perturbation grows in matter domination, implies two things. Even if we start from a very homogeneous and with very small perturbation universe early matter domination, let's say the CMB, they are doomed to grow with the scale factor. So gravity will collapse stuff, and structures will grow. And the other thing is, since all this assumes that delta is smaller than 1, even if we start with a delta that's smaller than 1, we will end up with a delta which is bigger at some point. Which means that perturbation theory will stop to be valid, and we need an analytic solution. Now, analytically solve GR in linear regime is very hard. And so what people usually do is, okay, let's take some symmetry assumptions. And this is exactly what is going to be done. And what is the favorite symmetry assumption of all physicists in the world? It's spherical symmetry. And spherical symmetry is exactly, as the name suggested, the basic idea of the spherical collapse that says, okay, we have a flat Friedman universe, but we have a small perturbation which is spherical of a certain radius r at early times. And we want to describe the evolution of just this system, small spherical perturbation on a flat background, so without other perturbations. So inside the sphere, we have delta or rho, which is actually some rho plus delta rho. And so there will be a slightly different h, or a slightly different, if you want, scale factor a will go in some a, and potentially there will be some curvature. So the curvature will go in some k plus delta k. Since we were assuming that outside the universe is flat, we can take the background curvature to be 0. Okay, so why I'm bothering with this? Because for a lot of time, at least. Sorry. Thank you.
This one needs to be
open. Why am I annoyed with this? Because when I studied structure formation for the first time, I always been told that all of this was just Newtonian. And that's a lie. You can do this in a fully general relativistic concept, because Birkhoff theorem essentially allows you to write independently the evolution of what's inside the sphere and what's outside in a fully relativistic concept. Even though there is a caveat, we are using Birkhoff theorem, which works in vacuum, and this is not really vacuum. But Weinberg said that it's possible to do that, and so I trust Weinberg. And if we fully trust Weinberg, we can set the problem like in a very simple way. So we have a curved Friedman-Robinson worker inside and a flat Friedman-Robinson worker outside. And that means that inside the sphere we will have some type of Friedman equation, like a dot square is equal to some 8 p by g rho plus some delta rho. And there will be some spatial curvature here, which I write delta k. And outside, instead, we have the standard Friedman equation, a squared, and outside we will have just a dot square is equal to 3 pi g rho. So the evolution of the two is independent, but at early times we are saying that the background is almost, the perturbations are very small, so we can actually require, at least at early times, that A is something like A plus delta A. And, okay, we already saw delta rho in this point, so delta rho is small, at least at early times. Now, we need another thing, which is rho is dust, so independently of inside or outside, we will have that it needs to dilute like the volume. So we will have that the combination rho a cube is equal to a constant, and the combination a cube rho plus delta rho is also equal to a constant. Now, we cannot arbitrarily renormalize A inside, because A inside, the scale factor inside the sphere is physically, its actual value is physically important because it's related to the radius of curvature of the shell. But outside, we can basically renormalize A as it pleases us. Usually in lambda CDM, we put A equals to 1 today. Instead of using this choice, Weinberg suggests, let's choose this constant in such a way that these two are equal. So rho A cubed is equal to rho plus delta rho A cubed. Okay. Now, why I'm doing all of this? The main idea is that if I now linearize this equation, so instead of having squared, I write it in terms of like at linear order, I will finally find the relation between delta k and delta rho. Sure. At early times, but so this is not a junction condition. This is just saying that inside and outside we have dust, and dust evolves as always scales with the volume. It's pressureless mass, so it scales with the volume. The junction conditions are actually imposed here somehow when we say that at early times at the border of the sphere and the background the behavior is very similar. And yeah, basically, I don't know which type of junction conditions could be used. I guess Israeli standard one, but like at the end of the day, we just say that delta A is small and delta rho is small at T roughly T0. I honestly don't see why, because basically this renormalization of A is A has no physical meaning, so I can just, in the standard Friedman metric, I can just rescale. Yeah. Excellent. So I don't think this is a junction condition. It's just a choice of coordinates in such a way that the scale factor I used in my Friedman ground is identical to the scale factor in the past. In the sphere, sorry. So why I'm doing all this stuff? Because if I, again, I can linearize this equation. And this is going to be something like, okay, I will try to do it properly and fast, which means that I will do it slowly and badly, but this is going to be something squared. Go to 8 pi g over 3 rho plus delta rho A plus delta A minus k squared and delta k. And now this is going to be, so that's squared plus 2 A delta A dot dot, and I neglect the higher order term. And here I get 8 pi g divided by 3. This was A squared. So I will have my rho A squared term as usual plus 2 rho delta A and plus delta rho is squared delta rho A squared. So this should be the linearized equation for delta capital delta A and delta rho. And now I can also use actually these linearized here. would write this a plus delta a cube, which is just a 1 plus the 3 delta a divided by a. Looks reasonable. And this is going to be just rho, which multiply 1 plus delta rho divided by rho, and this is going to be rho a cube. Delta a divided by a times a cube. So this will go away, and I get a nice equivalence. We should look something like delta a divided by a is equal to plus plus minus 1/3 delta rho divided by rho, if I haven't done anything wrong. So now I can plug these inside this equation, but since I'm going extremely slow, I'm going to give you straight away the spoiler. Which is going to be something like delta k is going to be proportional to 4 divided by 9 delta a squared. So why I've done all this stuff, and I apologize for doing it very slowly and having to skip steps to here, but really this is just plugging this information and this information on the linearized equation and solving. Because I'm saying that all the spatial curvature is actually mapped straight away into the overdensity delta. Delta is just delta rho divided by rho. Which means that since k is a constant, this is going to be true at all the times. And I basically mapped my perturbations in the curvature. And so I can solve analytically both the systems at the same time. And again, the revolution is independent. And that's delta k is the spatial curvature, so it's constant. It's not omega k, it's the omega k is usually delta k divided by a squared. Yes, there is a squared here. So this is a constant, and basically Weinberg suggests let's compute this constant at early times, so we can compute its value straight away from what is the density contrast, and then solve analytically this equation at all the times using that value of delta. So basically, little spoiler, we know that this matter will dilute, but the curvature will dilute slower because it goes as a squared rather than a cube. And so at some point, the curvature will start to dominate over this term, and this minus this will go to 0. So this sphere will expand. Initially, we're in the background. Then we slow down the expansion, reach a limit, and then begin to collapse. The moment in which a dot is equal to 0 is called turnaround. And what Weinberg does for us is basically tell us when the turnaround is going to happen, just knowing the initial overdensity delta A. So this is delta E of T0. Happy with that? Excellent. Because, let me switch off the light, if I find it. This is beautiful because essentially now we have an analytical solution that relates what is the stage of evolution of the sphere, this sphere here, compared to what would be the linear density contrast. So just the solution that grows as the scale factor A, or T to the 2 over 3. Which basically tells us, look, when the linear density contrast reaches order 1, so as soon as it becomes nonlinear, the shell stops to expand, and the physical density inside will be of order 5. Then a Newtonian argument that Weinberg indeed does not share and does not put in his book tells you that the realization of course when t is equal to b over 2, minus b over 2 because b is potential is negative. And so you get the v realization is equal to 1/2 v turnaround, which means that the radius of the realization is 1/2 of the radius of turnaround. And you can use all this information to find out that the density when the object realizes is roughly 180 times more dense than it was initially. So the density constant is 180. And interestingly, this is a linear density contrast of 1.7. Okay. Again, you can combine the analytical solution and write them in a parametric form and get basically the evolution of delta, the real delta, in terms of the stage of evolution. Turnaround is theta here, and realization is theta here. So this is, by the way, something that I did 20 minutes ago with Mathematica. It tells you that the evolution in the linear regime is the same for both this delta and the full analytical solution, but then of course they displace one for the other. The linear solution continues to grow, whereas the real solution stops and collapses. Theta. So pi, the solution of this system of equation, closed Friedman-Robinson-Walker, is given its parametric form. So you have an R, which is some constant that depends on the total mass. I don't remember which factor is here. Theta minus n theta, and then you have t. So you have r of theta and t of theta, which is this. Here is the energy, so it's k. Here is k to the 3 over 2 cos theta plus t0. So you just give the radius and the time of the thing in parametric form as a function of t. Exactly. Or the curvature, yes. Yes, exactly. Okay. Is everybody happy with this part? Because this is a bit annoying and boring, I do agree, but this is actually how we know how many objects in the universe will be collapsed at a certain time, because we just compute how long it takes for delta to reach some critical constant, 1.69 or 1.26. Okay, if everybody is happy with that, I can go to something very curious and interesting. All this stuff that I mentioned about Weinberg, you can do it at adding a very simple lambda here and lambda here. Okay, I canceled it already. And this is something that Weinberg did in 1987, so before the discovery of the accelerated expansion of the universe. And then he asked himself, how big can be this rho for this equation to emit, turn around, and collapse? Because if I have too much rho lambda, this curvature term will never be able to compensate the lambda, right? So there will be no slowing down and not stopping of the expansion. Or it will slow down, but eventually lambda could dominate over the curvature term, and so cause this shell to continue expand forever. So no structure would be formed in a universe in which lambda is too large compared to the primordial perturbation of delta k. And they knew something about the CMB. They knew that perturbation in the CMB, for what they were able to measure, were at least of order 10 to the minus 3. So they knew what was the initial spectrum of this delta k, or at least an upper bound. And so he did some math, which is exactly equivalent to the one I tried to show you now. Exactly the same stuff. Delta k is written as this delta I. Not really, because the size is related to delta. Yeah, okay. This rho tilde I is also, when I wrote this expression here, I cheated because I wrote equal to 4,9, but this is actually delta of t equal t0, and this is delta I of t equal t0. So it's the initial size of the object. So yeah, I cheated my way there, but it's true. You need also the initial size of the shell.
Okay, but it was assuming that it was new galaxy type, probably.
Yeah. I actually don't remember what he did in the paper at the moment, but it's interesting that at the end of the day, with this very simple calculation, you find this lambda here, which is only of 1 order of magnitude of the value that has been observed 10 years later or 12 years later. So Weinberg alone in his room found a bound on the cosmological constant which is competitive for current standards with the observed one 10 years later.
But it can be too negative, otherwise they can't be like a
Yes, so this works for positive, but you are absolutely right, you can use the lambda negative cosmological constant and have that all the structure in the universe collapse before matter domination, or like at the end of matter domination we will not exist. So yeah, this is just a curiosity, but I thought it's very neat, the question of how strong can be dark energy, and the answer being, if we exist, it cannot be too strong. Yeah, very neat paper. Okay, so as I mentioned, this is kind of at the basis of our understanding of structure formation. Now, actually, let me not use the board anymore for a bit, because what we do now, at least to analytically understand how many structures there will be in a cosmological volume, is to take the initial spectrum of perturbation, the delta, and then smooth out it in some volume. Now, this volume is usually taken spherical. It can be whatever. This is the window function that's equated it out on that volume. But to make it simple, we usually just choose one parameter, one physical scale, that will be the length or the physical scale of that smoothing area, smoothing region. So the main ingredient is the smoothed density contrast over this volume, which is just the space-dependent delta convolved with some window function. And if we use Euclidean spheres, we just say that the window function is this 3 over 4 pi r cubed. Now, why I stressed this Euclidean? Because once I spent roughly a month and a half of my life to see if spatial curvature of the sphere will change anyhow anything about the pressure performance, the answer is absolutely no. So don't do that yourself. If you were thinking about that, don't do that. Using Euclidean spheres is perfectly valid given the size of the objects in question. Okay, once you've built your delta, you can study the two-point correlation function, which, as Stefano told us this morning, contains information because the average of delta should be 0, but its variance is non-zero. And so you can build this sigma squared. If you conveniently choose r equal 8, it becomes sigma 8, which is one of the cosmological parameter, which is usually computed by large-scale structure survey. So sigma squared will be the variance of the density contrast, and since the initial spectrum of perturbation is somehow, okay, this is not really here, but as Stefano mentioned this morning, we believe the initial condition for the universe to be set by something that we call inflation. So inflation is responsible to giving the initial condition for the evolution of the universe. And basically, for this reason, any cosmological observable O can be written as some primordial density perturbation, so some P of k, which is the primordial spectrum of perturbation, times a transfer function, which is function both of the scale and the redshift. So for example, in the case of the correlation function, this transfer function will be just at least a linear scale will be just a d of z squared, the growth rate. Is this familiar to someone in the audience? Basically, if we are trying to count how many galaxies there are around, sorry, and there will be some beta, it will trace the initial density perturbation delta, and delta is usually written as a delta 0 times d. This d is a linear, thank you. This d is just a in matter domination, but if you have dark energy or radiation, the evolution can be slightly different. So this is your d of z. So if your observable is a correlation function of the type delta delta, you will say that, okay, you go to Fourier space usually because it's easier to use Fourier space because essentially the K modes are all independent one on the other. And then you will have that the primordial delta delta is just related to the primordial power spectrum of perturbation, P of K. That spectrum that Stefano showed this morning. There will be a B squared here, which is the galaxy bias, in the sense that you think that galaxies trace linearly the underlying dark matter distribution delta. And then there will be the transfer function, what it changes the amount with time, that is just this T squared term here. Is a bit clearer now? Excellent. So, this delta linear here, in this case, is used at linear levels, so we neglect any Eiger term here due to non-linearities. Thank you very much. And this is our approximation for the variance. So basically we say, for this to be valid, we better choose a K which is good enough to be at linear level still. And then we have our variance is just given by the power spectrum on this case, times the function. Okay, why is this important? Well, because I can ask a very sensible question. What is the probability of delta to be beyond a certain value at a given time? And since delta is a random variable, because this P of K is assumed to be Gaussian, and I have a variance sigma that I computed, then the probability is just a Gaussian, centered around the value delta that I want to find. And so what is the probability that it's bigger than a certain value is just the integral of the Gaussian. This specific value I will call delta C critical, and it's analytical, and it's the error function. Now, what is the probability that it has any value bigger than 0? It should be 1 because it's a probability, so it should be normalized. But it gives 1 out, not 1. So this is a bit of a problem. I will explain in a second how to deal with this problem. But either way, the idea is that since I have a random variable and I computed the variance, I should be able to tell you what is the probability of having an initial perturbation delta that collapses to a realized object nowadays. How does it represented picturized? This is your delta field in Fourier space, so there is a lot of different mode Ks overlapped between them, like so a lot of frequencies. You just choose a threshold, which is like a horizontal line, and you said everything above that horizontal line is going to be a structure. So there will be a realized object here, 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 and none of these will be realized. Does this make sense anyhow? Perfect. One-dimensional representation of this, you take your random variable, which is delta in this case. You do, this by the way is a very old plot, but I still like it. You do a random walk with a certain Gaussian variance, and these are many trajectories. Since delta grows with time, and as well sigma, the amplitude of the steps grows with time too. And then you say, okay, with time, I will have this barrier that indicates delta critical. As soon as a trajectory crosses this delta critical, it would be an object. And I forget about everything else in the trajectory. Now, this I forget about everything else in the trajectory was the stuff that Presse-Scherter didn't do in this expression here. And that's why the probability only was rounding out to 1/2. But if you properly account for the fact that this is a one-barrier problem, so you have this Fn here is just the amplitude of the barrier, and you renormalize the probability in this way, it normalizes to 1. I've been told, because I have not checked it myself. So this excursion set formula is called this way, basically allows you to find this probability and define this, which is the Halo mass function, and is the number of objects of a given mass m in the universe at a given time. And it only depends on the density contrast, the critical threshold for the density contrast, that, as we saw before, was just 1.79. So this way you can count how many objects there are in the universe, and this is surprisingly good as a model, because even if it's very rude, it's just saying, okay, everything is spheres and everything evolves in a rather understandable way. It works very well and describes results from both simulations and observations. Now, this solves half of the problem, because now we can count how many structures there are in the universe. There is the other half of the problem, which is how many voids. And the problem is not one-to-one. However, since the math that has been developed is very good, it is a very, very similar process. So you start with also a random walk. So when the density crosses a threshold, it will become a halo. But now you also have a lower threshold, negative delta, that will tell you if something has become a void or not. Now, how you do define a void? All these equations that I wrote can also be rewritten for with negative k. So you send this minus to plus, and you move from cosine to hyperbolic cosine and from sine to hyperbolic sine. And if you do the math, you get that basically inner shells expands much, much faster than outer shells. So at some point, the inner one will reach the border of the outer one before going to the Friedman background. The moment in which the innermost shell crosses the biggest one is called check crossing, and is it when the void is supposed to be realized. What's happening is essentially that the matter inside is pushed by the expansion to the borders. There is a deep over dense region that forms around the void, and so you have void, deep over density, and then the ground again. This value, by the way, the one in which the inner shell crosses the outest one, is when delta linear becomes minus 2.71. The real delta, yes, but the linear extrapolated delta will be minus delta 0 times a, so it can go to whatever value. By the way, this has been asked by 3 referees last time that I wrote a paper like this. The 3 of them said the paper is wrong because delta cannot go smaller than minus 1. I call it left handing. Either way. So it is now a 2-barrier problem, because you have a barrier that says this is a virialized object and a barrier that says this is a virialized void. These are the various configurations that can happen. It's a very complicated mathematical problem. Thankfully, Chet and this author managed to give me an analytical expression, or an approximation to this expression. That has been improved later by Jennings et al. In 2013. And so I can count how many voids there are in the universe, as well as how many halos there are of a given radius or a given mass. And this is basically everything we have about theoretical analytical modeling of large-scale structure. Then you have simulations, you have whatever you want, but like in terms of crude, raw analytical understanding, this is what we know. Okay. Yep.
So the critical collapse for void is the same for?
No, it's this minus 2.71. So you have that a random walk for delta, it crosses 1.7, it will become a virialized halo. It crosses minus 2.7, it will become a virialized void.
And it can cross both.
So you have a number of delta modes inside that volume. So basically you can have different trajectories going, like basically in this random walk you have a lot of stuff happening. So for example, this is a void in a cloud in the sense that this trajectory will cross and form some virialized objects, but then this random walk in particular went down, down, down. It means that you will have some small structure of these radii, but they will be included in a void of this radii, which is what's happening here. So you have a few clusters, sorry, it's the opposite. You have first the cluster forming, and then inside some void. So you have some clusters, but then a void inside.
And it still solves the dispersion set projected difference.
Yes, this is basically an extension of Prescherter for void. The original problem with this method is that it was not conserving volume, and that's why this formula is an improved version, because now the volume is conserved. The volume of voids cannot overcome the volume of the universe that you are counting the voids in.
In terms of volume, like there is higher quality, right? In terms of volume for these structures, there is the volume void is the largest volume. This has to do with the cosmic vector. So
Yes, indeed.
there's like is there since there is a conservation, there is a sense in which you start the flow of this is such that void and void become more and more dominant in terms of volume.
Yes, they have to compare two classes, of course. Even though, again, this was an initial problem in the first paper, because in this way they get too much voids in terms of volume. And so it needed to be fixed by this further development for Jennings et al. This is still very, very fresh, in the sense that every year there is someone that comes up with a new distribution functions for voids.
Yeah, the reason I'm asking is that people that work in cosmic cosmic vectors, they refer to voids, walls, filaments, and
Good.
cosmic web.
Cosmic web.
Texture web, actually. There's this, there's kind of a characteristic distances between those, right? I mean, these distances are conserved.
Yeah. Actually,
There's always like a 1/3 of distance to each one of those. There's only one exactly what is the proportion, but there's a kind of a conserved topology that means something in terms of distance. So even though changes with time, there's some conservation in the distances between those web forms.
so the shape of, sorry, no, keep going, sorry.
So is there a similar, I mean, in this picture here, things are always evolving and they're dominated more and more by voids. However, there's this, there's something that's being conserved. Is there a conservation of something that comes out of the differences,
So
or the description in terms of cosmic web doesn't see that and those are two separate things?
So this formalism and also the Prescherter underpredicts the number of large clusters or large voids and overpredicts the number of small ones. So this is an inherent problem of the formalism, which hasn't been solved. Now, I don't exactly know how that distance that you were mentioning in the cosmic web is done, but I'm very aware that, for example, Shesh at Portsmouth is doing a lot of cross-correlation between essentially voids and clusters. So when you cross-correlate delta voids and delta galaxies, this cross-correlation is very complicated because you can see galaxies, but you cannot see voids. So you have to infer with some void finder the distribution of the voids, and then you have to stack them. It's a bit complicated, but the idea is that voids do not need to be spherical, but once you stack enough of them, they should give you a spherical distribution. And deviations from this sphericity are Ricci space distortion that you can correct. At the end of the day, you get a solid estimated for this cross-correlation function. Now, when you plot this, it doesn't look like a power spectrum because they are clearly anticorrelated. And there is some power at some mod k, which is, so since the spectrum, let's suppose it's somehow related to P of k, the spectrum will, at linear level, will only evolve with time with d of k, but the shape will not change. So if you have a peak at some point at a certain distance k between void and cluster, this distance will not change. The moving distance between those 2 points will remain the same because it's not altered by the linear evolution. So I think somehow what you're referring is about this peak in the cross-correlation function between galaxies and voids.
Sorry for the big question. I vaguely remember there is a cosmic equation. Yeah. So can we use it as a cosmic rule?
Yes, I mean, if you can really erase the systematics from this stuff, you can use this cross correlation just like the turnaround equality in the power spectrum as a cosmic rule. If this is feasible with present data, I have no idea. Also, the point is the definition of a void, so using these void finders, they are... Yes, exactly. Yeah. Okay. Any other questions about voids and clusters? If not, I will try to go very quickly, since I'm super late, to why I think that this is very, very interesting. Because basically, the picture I'm giving you now is this picture of a Friedman background, which is populated by clusters and voids. Now, I ask you a sensible question. Do you think that this can be still described by a Friedman-Robinson-Walker universe? Because a Friedman universe is a universe filled with homogeneous dust and pressureless, so with no interactions between dust elements. At max, you can have linear order interactions between dust elements that are described by this gravitational potential and this delta I was talking about. The question is this still a Friedman-Robinson-Walker universe or not? Turns out to be a very, very difficult question that people have been exploring for many, many years, and this is at the main subject of cosmological creation. I will cite a paper from Edward Kolb, Valerio Marra and Sabino Terrese. Valerio Marra is a friend of mine, that's why I owe him to explain this classification a little bit. They proposed a classification of cosmological back reaction, which essentially stems from these three definitions. You can have a global background, which in the case of standard cosmology is Friedman, Robinson-Walker. Then you can have an average background. What does it mean, average? That I can take a slice of my universe, average all, so coarse graining, smoothing over any coarse graining scale, and it would be a new average background. And then I can have a phenomenological background solution, which is us with a telescope looking in this light coin, and then taking a solid average of this light cone, coarse graining, and then get again a background solution. If those three things are identical, there's no back reaction. Any other circumstance is a back reaction. So I wrote it in a Python statement. The reaction is true if the three definitions of average background or global background or phenomenological are the same. And then they classified if the global background solution is different from the average one, so the global is different from this inhomogeneous part where you're averaging, you have strong back reaction. If they are basically the same, but you have some back reaction induced to the fact that you are averaging along a specific line of sight, which is observer dependent, you have weak back reaction. To give a flavor of what this could mean, imagine a universe which is so-called Swiss cheese, so filled with voids and clusters, in which the voids are the holes in the cheese. And here there is a homogeneous Friedman background everywhere. This has been done in many, many different ways, but it's really called Swiss cheese universe. Now, you can be somewhere here. Since the whole universe in general is inhomogeneous, but when you coarse grain it becomes homogeneous, you have an average effect on, let's say, light propagation that, you know, here propagates in a certain way, then here propagates in another way, and so on and so on. These average effects of passing through a lot of voids, at the end of the day, changes the solution that you would have from no voids. This is strong back reaction in the Swiss cheese. Weak back reaction will be instead something in which there's no such a thing as this hierarchy void. You are just alone here, but you live in a void, and everything else is Friedman universe. Now, light propagation here is normal, so the background solution is identical to the average one, but since you live in a particular void, you will have some induced effect of photons climbing your gravitational potential within the void, and this is weak back reaction. Do not don't be angry with me, I didn't do this classification, this is from them, I'm just quoting it. So we have these basically two scenarios. What I will do for the next of the lecture tomorrow, because I already finished my time, is essentially give you a list of models that have been chosen to describe this sphere, so our local environment, so analytic solutions of this type of big back reaction, and at least one example of strong back reaction. Yeah, I think I'm at the hour, so I will stop here, but I can take questions if you have some.
We thank you at the end to get it together.
Okay.
So we could just have a few structures nearby.
Yes, it's basically cosmic variance.
It's kind of a weird situation where I mean, just see that only here we have some structure like that. Is there a version in which you can have weak back reaction, global homogeneous will not have strong back reaction? Because if you have voids like, take any one of these voids that cause weak back reaction, you make them spread out over the universe, would they not create a strong back reaction?
So
How can you live with
yeah,
not making
so I
a
would,
strong assumption about where you live?
my takeaway is that this the fact that you have phenomenological back reaction does not exclude the fact that you can have also average background solution that differs from the other one. So you can have both B and C happening at the same time. So now, how can you have C without B? Exactly. I can tell you that.
Ask for it, I guess.
Yeah, but the main, so I worked with it, for example, so I can give you a clear explanation. We live in this supercluster, which is called Lagrangian, and you can compute the correction induced by this supercluster from photons coming through you. Now, these corrections, delta, are basically proportional to some very weird integral of 1 divided by the differential h inside the cluster, scaled with the actual distance to the source. So if the source, for example, the supernova that exploded is very far away, these corrections are 0, or they go asymptotically to 0. So as long as you are having observation only in this region of the universe, you will see absolutely no back reaction because you are describing a background universe. And that's just because you don't have sources here or here. So for example, let's suppose that the universe is just us here, and we are looking at the cosmic microwave background. The corrections on those photons, since the distance is much larger than the size of the supercluster, will be 0. And so you are in a case in which the average solution for that cosmological observable is identical to the background one. Is the largest size is 150. And on Pantheon Plus, between redshift 0.023 and 0.15, so a relatively small redshift range, the impact of these objects are at mass, the highest one that I could find are of order 2%. Yes, the calibration, it's a much different subject, but calibrations are true distance indicators, so there's no, let's suppose that the calibrator is here. If I were to compute the distance from the Cepheid using the redshift, I should have some corrections because this is an integral from 0 to the redshift of the source. But with Cepheids, I don't measure redshifts. I measure periodic, like the period of the intrinsic period of the Cepheid, and that gives me the real D. That's why these type of effects don't change the calibrators. it's a much, much trickier problem if you have some calibrators inside and some outside. Because usually you combine different calibrators between them to get your big M, let's say. So in this case, there is still space. And actually, there's an interesting paper by Paula Bobel and Matthew Coles from ANU, in which they do this type of analysis, not with Laniakea, but with local voids or local dipoles in H for the Tully-Fisher calibrators. And they find no evidence of any variation in the calibrators.
But there's no evidence that you are inside of all.
Indeed. And actually, I would say the opposite, because otherwise we would be very unlikely to exist. But also, what is the effect of the cluster in that case, in which we live? And still they show that seemingly it's totally negligible. Now, all this back reaction stuff has been going around a lot to explain away lambda. So to say, we don't need dark energy, we just live in a void, and that's why apparently we see the accelerated expansion. Like all the cosmologists of my generation, I guess, I'm very convinced that lambda exists. Or at least something that behaves as dark energy must exist. So there is a lot of popular culture against back reaction problems, just because a lot of stubborn scientists have tried to use it to explain dark energy. But if you relax your bias, you don't want to explain away dark energy, actually back reaction can be quite relevant. For example, 2% order corrections are systematics which are much larger than, let's say, 3.
Every time you correct a particular velocity, so anything that you measure is not you're taking into account that stuff. It's not, I mean, it's just not callback reaction, but
Yeah.
it's a phenomenological correction that has to do with the inhomogeneity and small scale,
Agree.
it's not called this. It's just a direct effect that doesn't properly limit the dynamics. It's just,
That's the point. It's just kinematics, which means that basically, let's suppose that I live here and in a cluster, so here is more void. A supernova here will be pushed away by the void, and so you will have a peak, V peculiar, and I can account for this V peculiar when I change the redshift of the supernova. But I'm not accounting for the fact that also the space between this point and this point is stretching differently, because we live in a void, and that's not accounted for by peculiar velocity correction, which is why I did all this stuff on Laniakea to show that you should keep it into account and gives you a systematics, which is small, but is still non-negligible. But for people that didn't read the paper, tomorrow I will explain a bit better what I've done in that particular circumstance. I thank you very much. Sorry if I did mess it up a bit on the blackboard.